All right, now let's work on figuring out the electrical potential of this system. So here's our reaction that we already came up with before. We've got copper 2 becoming zinc solid and reacting with zinc solid to become copper solid and zinc 2. Now, just as a reminder, we got those by looking at our data booklet. So on this screen, you would have found copper 2 positive, you would have found zinc. Remember, the copper reaction is the strongest OA, so we wrote its reaction forwards. And the zinc is the strongest reducing agent, so you wrote its reaction backwards. Now, what you haven't seen, or we haven't used up to this point, is this column right here on the far right, the electrical potential. Each of these half reactions has an electrical potential. So, if you go and look at copper's potential, you will see, I'll actually give you a second to find that. You can pause the video if you need to. Its potential is a positive 0.34 volts. Okay? And since we wrote the copper reaction forwards, we leave that voltage alone. We're just going to copy it down exactly how it is in the data booklet, whether it's positive or negative, we're just leaving it alone. Okay, now go to your data booklet, pause the video, find the zinc half reaction, and find its voltage. Once you found it, because we wrote the zinc half reaction backwards, we're not going to write the negative 0.76 like we see in our data booklet. We're going to write a positive. Because we flipped the reaction, we're also going to flip the voltage. So now that's a positive 0.76 volts. Okay? Which means because we could combine these two half reactions, we bounce the electrons and combine them, we can also combine these voltages. So that means that this cell has a positive 1.10 volts. Now we call that the, sometimes they'll call that the potential difference. Or sometimes they'll call it the potential voltage. Essentially, that's a way of saying under the perfect circumstances, how many volts could this system produce. So in this case, this one, if everything is ideal, could produce up to 1.10 volts. Now, a Duracell battery or an Energizer battery, like a AA, AAA, C, D batteries, those are all 1.5 volt batteries, and I'll show you the half reaction for those here in just a second. But that's what they would produce. This one is a 1.10 volt battery. Okay, couple things to remember. The keys here are you write the OA reaction forwards, so you leave that voltage alone. However it is in the data booklet, just write it. The RA, though, you write backwards. It's over here on your table. So you write that reaction backwards, and you're going to flip whatever that voltage is. So like the zinc here, we didn't write negative 0.76, we wrote positive 0.76. Then you can add them. The other thing you need to write in your notes, somewhere around this, wherever you have room, put a big star by it, but you're going to write never multiply voltages. So, for example, let's say that in order to balance this, I had to times this one by 2. Now, don't write that in because we don't have to in this case, but let's say I did. I would not times the 0.76 by 2 because it doesn't change what's going on, it just changes how much of it there is. Okay? Let me show you some. All right, I just grabbed a couple of batteries here. So here's a D cell battery, and here is a AA. Okay, these have exactly the same voltage. This is a 1.5 volt battery, and this is a 1.5 volt battery. The only difference between these is how much stuff is in there. So if you were to hook this up to a flashlight, or you hook this up to a flashlight, there's no difference in the amount of voltage they produce, but this one's going to last a little bit longer, and it might be able to produce more amperage, which you don't need to worry about. But the voltage will stay the same. This one will just do it longer because there's more stuff. So just like above, I said don't multiply the voltages. This is the reason why. This and this have the same voltage. This one just has more stuff. Okay? Does that make sense? Hopefully. Okay, let me show you this. On page 8-3 in your notes, you can see on the part right here, this is basically a cutaway of what the inside of one of these batteries would look like. So the half reaction is right there, this one. So it's actually a zinc case. The metal case is zinc. The inside, the paste, is this half reaction right here, this manganese oxide reacting with ammonium ions. And that reaction produces 1.5 volts. So that's what's going on inside one of these. Now, to get different voltages, you either have to use different compounds, like different chemicals that would give us a higher voltage, or just more of the same one. And that's what's going on up here. So you can see there's a set of 5 beakers there. So kind of like in the diagrams that we've done, if you chained a bunch of those beakers together, if each one of them gave you 1.5 volts, you would get more. So in this example right here, you're getting 9 volts. And that's what this diagram on the side over here is showing, that you have, instead of just one cell that produces 1.5 volts, inside of a 9-volt battery, you actually have 6 cells, each of them providing 1.5 volts. So 1.5 volts times 6 is 9 volts. And that's actually, I do not recommend you do this at home, but if you take a 9-volt battery, you know, the kind you test by sticking it on your tongue, if you break one of these open, what you actually have inside is 6 little tiny batteries piled on top of each other. So these produce a lot more voltage, 9 volts compared to 1.5 volts. But if you had to draw voltage, this one would last much longer than this one, because this is really just 6 batteries that you're using all at the same time. Okay? Now, you guys may have never even seen one of these, but this is a 6-volt battery. When I was younger, this is what was in a lot of high-powered flashlights, which by today's standards are probably weaker than what's on your cell phone. But either way, they were big, boxy lights, and you had to buy these great big batteries in order to power them. And this is actually, even though it's really, really large, is only a... Where did it go? Right there. It's only a 6-volt battery. So I thought it would look maybe something similar to the 12-volt battery, but when I opened it up and pull out this carbon, again, don't do this at home. Be safe. If you open this up, I found something that's apparently stuck. There we go. All right, I found something interesting when I opened this up. And this, I'm guessing, is a way to cut costs on terms of the company. I expected something like this. Instead, what I found were a lot of these. And I mean literally, they just put 4 D-cell batteries inside of a metal case, put a cardboard lid on top of it, and sold it for way more money than you would have paid for the D-cell batteries. So, more voltage, you can either change the chemicals in the half reaction, or you change the number of these. So, if you've got a remote and you've got to put 4 of these in, that means that remote probably needs 6 volts in order to run. If you need more or less than that, that means you could run your remote off this. That would not be fun. but you might not lose it. Anyway, so that's what's going on. You've got different cells, different options, different ways to do it. Let me bring you back to this view, maybe. All right, don't need the drawing anymore. In your notes, you'll also notice down below, oh, sorry, this is what we call a primary cell, meaning it's non-rechargeable. It's just a normal battery. These batteries are called secondary cells. Any type of battery that can be recharged is a secondary cell. So in essence, the half reaction here would produce voltage, and out of the negative terminal of the battery, let me just draw this quick. Let's say this is a car battery. If this is negative and this is positive, we know that electrons would flow out through your car and then back into the positive terminal of the battery. Now, when you start your car, though, it's going to do this. It's a voltaic cell, and it's running. However, an electrolytic cell, which we'll learn more about later, is once your car is running. Once your car is running, you don't need the power anymore. You have something called an alternator that's actually generating power as the engine runs. So now we start pumping energy back into the terminal, going opposite the way it wants to go. And what that does is, if we think back to our drawing of the zinc electrode breaking down and the copper building up, now we force the electrons to go the other way, and we force them into the zinc, which causes the zinc electrode to start to build back up and the copper electrode to start to break down. So basically it's a way of recharging the battery. So any type of battery that's rechargeable we call a secondary cell, just like this. Hydrogen fuel cells are down here at the bottom, and I'll probably do a whole separate video on hydrogen fuel cells. They're really no different, but they're really interesting, and they tend to show up a lot on the diplomas, which you guys don't have to write this year. If I use this video for future years, you do have to. But the hydrogen fuel, that one, the hydrogen fuel cells are something I'll cover in another video, because there's some pretty cool stuff going on and some really cool potential for clean energy, possibly. All right, so that's pretty much it for the lesson. So here's what your homework is going to start with. You've got these setups, and what they're basically showing you in this setup is that this electrode is this one right here. This one is right here. You'll notice that's a carbon. Remember, that's an inert electrode. It's not involved in the reaction, so don't spend a bunch of time looking for it on the table, because it's not there. Then these are the electrolytes, right? This would be in that solution, and these two ions would be in that solution. They don't show it here, but you know you're going to have a positive and a negative inside that tube. Down at the bottom, what you need to do is list here who are the electrodes. So in this case, for example, copper is one of the electrodes, copper solid, and carbon solid is the other. The electrolytes, the same thing. You'd list copper 2, dichromate, and H positive ions. Below that, you'd write your reduction half reaction, right, for your strongest OA. You'd write your oxidation half reaction, and then your net reaction once you balance the electrons and combine them. From this point on, now that you know how to do the voltage, you should also be including the voltage. So when you do your reduction half, put that voltage. When you do your oxidation half, put that voltage. When you combine them to give the net reaction, you should also put the net voltage. Okay, so make sure you're filling those out. You should also follow the same kind of guidelines that we did for our other diagrams. For example, I messed this up. Dang it all. That's okay. There's one more thing I got to do another video for. I just realized. But then it'll make this part make sense. You need to show the electron flow. You need to show the anion flow. You need to show the cation flow. And you need to label your anode and your cathode. So That'll make more sense after I show this other video. Sorry for the mix-up. That's it for this one.